Okay, so let's get going. So yesterday we introduced these orbital angular momentum operators, the three of them, the three components of x cross p, and divided by h bar to make it dimensionless. And we can make the total angular momentum operator L squared by squaring the individual components and adding. We established these results that the commutator of, for example, Lx with y is I times z. So and similarly, if you do a commutation with Li with Pj, I haven't written this down here, you find I times Pk times epsilon, sorry. So for example, Lx times P commuted with Py would be I times Pz. And basically what we're learning here is that L commuted with the component of a vector operator gives you the third vector operator in that set. And from that you can go on very easily to show it. The demonstration is exactly the same as what we already did with the angular momentum, the total angular momentum operator, that any of these orbital angular momentum operators commutes with scalars like x squared or p squared or x dot p. Also, L squared commutes with any of these things, any of its components. So we have a situation so far which is precisely analogous to the commutation relations to the total angular momentum, what we have so far called the angular momentum. Operators. So for example, ji, xj, commutator is I sum over k, epsilon I, j, k, x, k, etc., etc. So we have that ji, jj is equal to I sum over k, epsilon I, j, k, jk, which mirrors one which I didn't write down up here and should have done, which is that li, lj commutator is equal to I sum over k, epsilon I, j, k, lk, which is really a generalization of this rule, an application of this rule here to the vector lj being put in here, so lk appears over there, which just says that L is in fact a vector operator, and similarly, this is a generalization. So we have this exact analogy, and the question obviously arises, are they the same operator? Is L the operator which are the operators Lx, Ly, and Lz, the operators that generate rotations that we inferred had to exist just by thinking in the abstract about rotations at the end of last term? And so the answer to that question is no, and here is the demonstration of it. Let's calculate j squared, comma Li. In other words, let's work out the commutator between the total angular momentum operator and one of these components. Then this is going to be, this is a commutator of a product, and I need to write this. This is a sum of squares, so I need to make that explicit. So I write that as the sum over I, say, of ji squared, comma, oops, no, I won't do because I've got I busy, j li. And now each one of these is just a simple product, so we use the rule for taking a commutator of a product. So this is equal to the sum over j still of, that's a j, what we're summing over. I leave one of these standing idly by whilst the L operator commutes with the other one. And then I have the L operator commuting with the other one, the first one, while the other one stands idly by in his position. Now we know what the result of this is because this is a vector, and we established last term what the commutator of J with the component of a vector is. It's going to be the third member. So this I can replace by an epsilon Ji, say k. So this is going to be a sum over J, and then there is going to be a sum over k coming up of Jj. There will be an I from the commutator. So Jj, that's this one here. Make sure that's clear. This is going to be epsilon Ji k Lk. So that's the fundamental rule we established, that the commutator of this with any vector gave you the third component. And then here we will have the same thing, epsilon Jik times Lk times Jj in the back. So we can clean this up into the I times the sum over both j and k, going from over x, y, and z, of epsilon Jik times Jj Lk plus Lk Jj. And so this is the sort of thing which often vanishes because this is anti-symmetric. If you swap those two over, j and k, you get a change of sign. And if this were symmetric, we would get a change, and if this were symmetric in j and k, in other words, if you swap them over, you got no change of sign, then you just got the same thing back, then we would have, zero. But this is not symmetric. If you interchange the order of these, if you swap the indices, so under a swap, what does this go to? It goes to Jk Lj plus Lj Jk, which is not the same as this. So this thing is not equal to 0, but we know that j squared does commute with all of its components. So that sort of suggests that these are not the same thing. So let's try and understand what these operators, these orbital angular momentum operators, and really understand their relationship to the things that generate rotations. So now we need to talk a little bit in abstract about rotation around a path, motion around a path. So if we just have a translation, we've already studied translations last term, through one displacement, A, that's generated by the unitary operator, which we called U of A, which is e to the minus I A dot P on H bar. Right? That is the operator which generates out of a state, the state that we would have if our system was shoved along the bench by, or was at the different location, a distance, a vector displacement A away. So let's consider the following. Let's make a series of displacements. Here's a 1, here's a 2, here's a 3, and so on, right? We're going to make a path by doing a series of displacements. Then we have that U total is going to be the product of this displacement and this displacement, this displacement, this displacement. So it's going to be U A4 operating on the result of using U A3, operating on the result of using U A2, U A1. Each of these things is an exponential. So this is e to the minus I A4 dot P over H bar e to the minus I 3 dot p over h bar, etc. And the operators occurring in these exponentials all commute with each other because all momentum operators commute with all other momentum operators. They commute with themselves, obviously, and the px commutes with py, etc. So when we multiply these exponentials together, we have the usual magic of exponential functions. We don't have to worry that those are operators. So these are operators, but we don't have to worry about that because everything commutes. So this can be written as e to the minus I, the sum of these vectors, summed over I, dotted into p over h bar. So the operator that generates you as the state that you get as a result of all of these displacements is given by this. Just a single exponential. It's just one of these. It's an operator of exactly the original form, where the displacement is simply the sum of them. So the result of taking it this way and this way and this way and this way, we've just shown, is the same as the result of just taking it in a straight line over the sum of the AI. So that's a general argument. And now we say special case. So in particular, for a closed path. So if the path carries you all the way around, what does that mean? It means the sum of the AI is 0. All the vectors add up to nothing. And that implies immediately that U total, because it's e to the nothing, is the identity transformation. Now that might sound obvious, but you'll see in a minute that that's anything but an obvious result. So, so now let's specialize in our paths. Let our path be made up of a series of so let this be x. Let this angle in here be delta alpha. Let n be the unit point out of board. Then this vector here, this displacement vector, this is going to be A equals delta alpha n cross x. Right? That's just ordinary classical geometry. That if I go like this and n is out of the board, then that's the displacement that we generate. So what does that do? That means that the unitary operator that moves my system from here to here, U delta alpha, is going to be e to the minus I a, which is that, delta alpha n cross x dot p upon h bar. So that's just applying the standard stuff with the displacement vector of this form. This is delta A, or A, whatever. But what is that? This scalar triple product can be reordered, sort of standard vector algebra tells us that we can reorder this thing into n dot x cross p. So this is equal by vector algebra to I delta alpha n dot x cross p upon h bar. So that's the operator, okay? And there's the h bar that's here. But this is what we define to be L. So this is equal to e to the minus I delta alpha n dot L. So that's what we've now discovered, essentially what L does. L is the generator of rotations, of movements around circles. So we conclude that L is the generator of translations around circles. We can also get something interesting, very important, by combining these two things. So for a complete circle, so for we can multiply these things together. So U for a circle is going to be the sum of this for all sorts of delta alphas, okay? E to the minus I delta alpha n dot L, which is going to be E to the minus I alpha n dot L, where this is the sum, sorry, it's going to be the product of these. Right, if we make a series of transformations, each one by delta alpha, then that product of these exponentials can be written as the exponential of the sum of the arguments. The sum of the arguments, it always had n dot L as the operator, and the sum of the alphas, of the delta alphas, we're going to call alpha. So for a circle, this is going to be 2 pi. So we're going to come to the conclusion that e to the minus 2 pi I n dot L is equal to the identity transformation, because we've shown that U going all the way around in any closed path has to be the identity. So this thing has to be an identity for any vector, any unit vector n. And we'll need that result shortly. And what do we, come on. So what is the general picture here? We can now understand what the distinction is between orbital angular momentum and angular momentum. So here we have so look at this L, and then there's this arrow here. So we're moving the point at the base of the arrow around a circle. We're just translating it. Let's just go back. So we're just moving it round a circle, but we're not doing anything to its internal structure. We're just translating it. So if it has a little arrow, it has an orientation, as for example the direction of its spin, that's not going to change its direction. It'll just be carried round. Now ask what J does. What J does is it makes you the system you would have had if you took what you've got and you rotated it on a turntable around the origin. If you rotate it on a turntable around the origin, this is what happens. The orientation of the particle changes as well as its location. So J is changing locations, L is only changing locations. J is doing a complete job by putting the particle on a turntable and rotating it at the same time as translating it. That's the difference. Right, so we've got these operators, and we want to know, obviously when you have operators, you need to know what their spectra are, what the allowed values of their eigenvalues are, and we can now immediately say what these are going to be. So we know that we can find a complete set of simultaneous eigenstates of L squared and any one of its components, Lz. That's the same as when we were dealing with the angular momentum operators. And we obtained the eigenvalues of the angular momentum operators at J squared and Jz by exploiting the commutation relationships between the different components of J. That was the only thing we used, right? So we got that the E values of J squared Jz were J plus 1 this is for j squared. J squared had eigenvalues of j plus 1, where j was 0, a half, 1, 3 halves, etc., right? And we had that jz had eigenvalues m, which lay between minus j and plus j. And we got these results only using that ji, comma, jj equals I epsilon ijk jk. If you look back at what we did, you'll find that that's the case, that nothing else went into this but these commutation relationships here. For the L operators, we have the same commutation relations, right? So the L satisfy identical commutation relations. So the argument we had for J could be repeated line by line. There's no point in repeating it literally, but virtually we now repeat that argument line by line with every J replaced by an L, and we conclude that the E values can be L squared has numbers like L plus 1, where L could equal 0, a half, 1, blah, 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 and LZ has M lying between L and minus L. But then we think, so these are the candidate, no other numbers are possible than those numbers, right? That's what that argument shows. Are all those numbers possible? No, for the following reason. But e to the 2 pi I Lz has to be the identity operator. We've just shown that. That's this statement with n put equal to the unit vector in the z direction. Okay. So actually, I need a minus sign. So we have that this thing has to be the identity operator. Consequently, if we use this operator on one of our states, which are going to be called Lm, right? This is the mutual eigenstate of L squared and Lz with eigenvalue LL plus 1 for L squared and M for Lz, precisely by analogy with the with what we did with J, then this has to be simply Lm. Because this is the identity operator. But what actually is this? If we have, so we're doing an exponential of this operator. This operator looks at this and says that's my eigenfunction, and therefore it replaces itself with the eigenvalue. So this is e to the minus 2m pi I times Lm. Comparing this side with this side, we have that e to the 2 pi I m is equal to the number 1. And that implies that m is an integer. Because if it were a half integer, this will be e to a certain number of I pi's, which would be minus 1. But we've shown it cannot be minus 1, so it's an integer. So this is where there is a difference between what happens, between what L does and what J does, and why we have to keep track. So L is looking very like J, but it is not J because it is, well, we've seen physically that it's not, because it merely translates you around a circle. It doesn't rotate you around a circle. And that has the consequence that m has to be an integer, and therefore L has to be integer. So the eigenvalues of L squared are LL plus 1, where L equals 0, 1, 2, 3, 4, etc. And therefore m is also going to be stuck on integers. So what's happening here is that what we learn from this, in some sense, is that let's just do this again. So it's when we have translated our system all the way around a circle, it's come back to where it was, same orientation, everything the same, right? And the result is that an identity operator is applied, as described by applying an identity operator to our state. If, on the other hand, we translate J all the way around the system, you would think it came back to where, well, it comes back to the same place, undoubtedly, and the little arrow comes back to the same orientation, and you think you were back in the same place. But quantum mechanics is telling us, well, it's really experimental physics tells us that it's not. How do we know? So that arrow, I'm having to describe the orientation of the spin of a particle using an arrow, and I've already said this is a hazardous enterprise, because in quantum mechanics, particles are gyros, and they, in some sense, have a spin that points in a direction. But you do get into trouble, as the Einstein-Podolsky-Rosen experiment shows, if you take this idea of pointing in a direction too seriously. And here we have another example of the risks of taking too seriously the idea that you can describe the spin of a particle by pointing in a direction. Because when it has gone all the way around, the state vector has changed sign in the event that this is a half integer. And for and the Stern-Gerlach experiment and other experiments, zillions of experiments, show that electrons and protons and so on do have half-integer values. Their angular momentum comes in half-integer amounts. So when you take a real electron on one of these tours around the origin, its state is somehow different from the state it started from. It's difficult for us to understand that. But that's what the mathematics combined with the experimental physics tells us. Okay. So the next item on the agenda is the eigenfunctions of L squared and Lz. So we already know what the eigenvalues are. What we now would like to know is what do these states look like, these LM states look like in the position representation. So what we're trying to find, so what we want is R theta phi LM. We'd like to find expressions we'd like wave functions which describe these things here. And our strategy is basically that we're going to, so the strategy is this, the detail is rather tedious, but the strategy is this, we are going to apply L plus to LL and get nothing. We're going to express this abstract, so this is Lx plus, this is, all right, I think we talked about this yesterday, but I'm not absolutely certain, Lx plus I Ly. So this is the operator which will try and raise the M entry here to one larger, but that's not possible because it's already its largest value, so it'll kill it. So this is an operator equation. We will look at this operator equation in the position representation, and then it will become a first-order differential equation. We will solve it. It'll turn out to be dead simple to solve. So that will lead us to. Let me leave off the R because we're not really interested in R for the moment. It will lead us to this, LL. And then we will be able to say that theta phi L minus 1 is equal to theta phi, sorry, there's a horrible square root now, L plus 1 minus M minus 1 times L minus this will lead to the minus 1 times L minus So we will, having obtained this wave function, we will apply L minus to it in the position representation. That will give us essentially the next one down. That will lower this by 1, and by repeatedly doing this, we'll be able to generate all of the wave functions associated with a particular total angular momentum quantum number L. That's the strategy. To carry this out, what we need is expressions. We need expressions in the position representation for these operators. So this... let's start by writing down what Lz is. What is Lz? It's 1 over h bar of x py minus y px. In the position representation, what is that? Py in the position representation is minus I h bar d by dy. So this becomes minus I x d by dy minus y d by dx. Now, to find out what that is, we would like to express everything in terms of theta and phi, because we know angular momentum is to do with rotations. That's why we want to use theta and phi, spherical polar coordinates. And we could just use the chain rule to turn this into derivatives in theta or phi, but it's much easier to use the chain rule, not going from this to d by d theta, d by d phi, but to find out what is d by d phi according to the chain rule. It's dx by d phi, d by dx, plus dy by d phi, d by dy, plus dz by d phi, d by dz. Right? That's just the chain rule from calculus. Now we put in what these x, y, and z are. We know that x in polar coordinates is r sine theta cos phi. We know that y is r sine theta sine phi. And we know that z is r cos theta. So this implies that, so take a derivative of this with respect to phi. We have that dx by d phi is going to be minus r sine theta sine phi, which is the same as minus y, is going to be simply minus y. We have that similarly dy by d phi, that becomes a cosine, and therefore this becomes x. And we have that dz by d phi is nothing at all. So we take these results and stuff them back in here, and that tells me that d by d phi is equal to, that's a y, sorry, that's a minus y, so let's write it down, minus y d by dx plus x d by dy. What is the relationship to what we have up there? That is, okay. So this is precisely what's in that bracket for Lz. So this implies that Lz is minus I d by d phi. Of course, this is no surprise, because Lz is the thing that rotates you around the z-axis, and everybody knows that the spherical polar coordinate is defined as the angle around the z-axis. So it's kind of obvious that this has got to be the case, but it's nice to see that the chain rule delivers the goods. Now the next bit is distinctly more tiresome. What we now have to do is, what we want to do is, as I said, is express L plus and L minus, Lx plus L, plus ILy in terms of d by d thetas and d by d phis. You could go at this just by brute force, but the algebra would be heavy, and the algebra is not going to be that wonderful now. Here is, I think, this is the way to do it. Right, so let's just calculate what d by d theta is using the chain rule. It's obviously dx by d theta d by dx plus dy by d theta d by dy plus dz by d theta d by dz. Okay, we have expressions up there. So dx by d theta is going to produce us an r cos theta, cos phi, etc. This is going to produce us an r cos theta, sine phi. So I got a common factor of r cos theta, open a bracket, and then we will be able to write down cos phi d by dx plus sine phi d by dy. And then finally we have dz by d thingy, which is going to be minus r, because we're differentiating cos sine theta d by dz. Now let's take our expression for d by d phi and multiply it by cot theta. So we're going to write down cot theta d by d phi, just for the fun of it. So this has to be, we're going to in doing it, we're going to replace, well, let's take this one first. It's going to be r, that is r sine theta cos phi. When we multiply by cot, which is cos over sine, the sine is going to go into a cos. So this is going to be r cos theta brackets sine phi, cos phi d by dy. So this here is r sine theta cos phi, which is x, times cos over sine, which is cot. And then that y is going to be r sine theta sine phi, and this cot multiplication will turn the sine theta into a cos theta I take out, and we will have a sine phi here, d by d how much? X. That's it, right. So what we now do is, just again for the fun of it, we take d by d theta and add on I times this. So we look at d by d theta plus I times cot theta d by d phi. What happens then? We have r cos theta as common factors. Oops. Quick. I should have, yeah, excuse me, yes, that's right, that's fine. I'm looking at the wrong coefficients. So what am I going to be doing? I'm going to be adding this and this. So we're going to add I times this to that, so with a common factor of d by dx. So we're going to have cos phi minus I sine phi, which is well known to be written as e to the minus I phi. That's how much of d by dx we're going to have. And then we're going to have sine phi plus I cos phi, and that is going to be plus I times e to the minus I phi d by dy. We haven't quite finished, have we? Right, so if you expand this out, it's going to give you an I cos phi, which we want. That's this one here, times I. And it will contain a minus I sine phi times an I, which makes it a plus, just plain sine phi, which is what we want there. Then finally, we've got this in the back. So we're from here, so we have minus R sine theta d by dz. Yeah. So supposing and this thing could be written, r sine theta is this. No, leave it alone. So what we do now is we multiply this by e to the I phi. So we have e to the I phi brackets d by d theta plus I cot theta d by d phi, which will turn out to be our bottom line, is equal to, this is going to be cancelled because I'm multiplying through by e to the I phi. This will be cancelled. So we will have r cos theta brackets d by dx plus I d by dy. And then we will have minus r sine theta times e to the I phi, which I choose now to write as cos phi plus I sine phi. And now r sine theta cos phi is x, and this in the back is going to be y, r sine theta sine phi. So we'll be able to write the right-hand side as r cos theta d by dx plus I d by dy minus, so this is going to be x plus iy. Excuse me, this was times d by dz, it always was. Where did that get lost? It was minus r sine theta d by dz. Yes, it just got lost between this line and this line. Okay, phew. So I want to now establish that that is actually L plus. So in order to do that, I write down, so what is L plus? L plus is Lx plus I Ly. Don't need those brackets. Which is 1 upon h bar. Okay, what's px? It's y pz minus z py. Plus I times Ly is zpx minus xpz. So now I want to turn this into d by dx's. So this will be, so this is minus ih bar d by dz. So we're going to have, no, let's just, sorry, before we do that, let's gather things together because we've got a pz and a pz. So let's just for the moment write this is 1 over h bar. We're going to have, a common factor of z. We're going to have I, z, px plus I, py, I think. Right, this I and that I make the minus sign that we have there. Z is the common factor. All right, and then what about the z factors, the pz factors? Well, we have a plus y minus ix pz. Now we replace the p's by minus ih bar d by dx, etc. So we'll get a minus, the h bars are going to go throughout. From here we'll have a minus I times an I, which will give us a plus. So we'll have a z d by dx. Here we will have, we have two i's making a minus sign. We have another minus sign coming in from the minus I. So we end up with minus I d by dy. I'm rather worried by the sign there. The two i's made minus. No, the two made a minus and I soaked up. Sorry. These two i's made a minus. I brought in another minus from minus ih bar d by d. The minus is cancelled, leaving me only with the I. And this is going to bring in a minus I. Well, so we have a, if you propagate this minus I inside here, we get a minus sign there. So we get a minus x, and this is going to be plus iy, because there's a minus I here, and there's the minus sign, and here's the I, d by dz. And that, I hope, agrees with what we have written. It does, because r cos theta is also known as z. So we have z d by dx plus I d by dy, and here we have a minus x plus I y d by dz. So we have established a very important result, that L plus in the position representation is the differential operator e to the I phi brackets d by d theta. It's plus, isn't it? Plus I cotangent theta d by d phi, close brackets. There is an analogous calculation, which I'm not jolly well going to do, which tells us that L minus is equal to minus e to the minus I phi d by d theta. Is it minus? Yeah, it is. Minus I cot theta d by d phi. And if you try and do the two calculations together with plus and minus signs, good luck to you. It's fantastically confusing, right? So at least I got one of them right. So those will be our. Well, let's leave it at that. Those are going to be our starting points for tomorrow deriving the eigenfunctions of these very important operators.